Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program. Local broadcast is made possible in part by Pfizer.
So I want to welcome everyone here today. There may be a few new people joining us. I realize I'm not competing against the Michigan football team. And so for those of you that wanted to see Purdue in Eastern Michigan and didn't want to see me, I welcome you today. You have a little bit of catching up to do. We've had 2 lectures so far that have discussed lenses and how they work, and then how to get the proper exposure. Today we have an explosion of science. Even for the people who've been here the first 2 lectures, we're going to have more science. Your head's going to just be like this when you walk out of the room. So there's a lot to do. We got to get to it. And we'll finish up on our lecture series today, but have a slight continuation then with a similar topic next week, and I'll get to that at the very end. So briefly, I covered lenses in the first class and focus, and then in the second one we did exposure, which had a lot to do with the shutter body. Today we're going to work on the subject. The subject has a lot to do with art, but it also has a lot to do with science. That being, in a trivial sense, what you're taking a picture of is light. If you didn't have light, you couldn't take a picture. But actually, it's far, far deeper than that. If you ask a professional photographer who's an art photographer, what are you trying to achieve? They'll say, it's all about light. And that's the title of this talk. And so, both in a trivial sense, we photograph light intensity, but in a very deep artistic sense, what we're trying to do is look at light. So, all of you should remember this who attended the second lecture, The Holy Trinity of Photography. It's about getting the proper exposure. How do we get the right amount of light? How do we use it artistically for the depth of field, or how the look is going to be? We're talking today not about the quantity of light, but the quality of the light. What does it mean to have a good quality light or a bad quality light from a photographer's point of view? Photography comes from the Greek to write with light. That's what you're doing. You are writing with light in some sort of recordable media, whether it be a CCD detector, as we talked about last time, or film. That's what you're doing, is writing with light. And today, we're going to be discussing that. So first, we have to start out with what is light. I could spend an entire semester lecturing on light and never cover any of the aspects that I'm going to be talking about today. In fact, I have taught light numerous times in classes, and all the slides I'm showing you today are new. So light is a many-faceted subject, and we're covering just a particular part of it today. Light is a wave. Okay, we're all pretty familiar with waves. But whenever I ask my class to define a wave, I get people writing down sine and cosine and other stuff, and that's not a definition of a wave. It's perhaps a mathematical description of a wave, but they don't come up with what a wave is. A wave is a propagating disturbance in a medium. I make a disturbance, and it propagates. It moves. Now, what's so fascinating about light, and which perplexed scientists all the way up until the beginning of the 20th century, was this: a wave is something that propagates on a medium. Light gets here from the sun. There doesn't appear to be any medium in between. And so very intelligent, very respected scientists hunted for what would be the medium that's out in outer space, that permeates all of space that light travels on, just like that rope. Just like in a waterway, you can't have a waterway without water. What is being disturbed when you have light? Turns out light is special. It doesn't require a medium to move. It moves through the vacuum. There is nothing between the sun and the earth. It's vacuum. Largely speaking, there's nothing there. And that light doesn't need anything. It makes its own medium as it goes. That's a very special property of light. So light is a wave. Now, you've no doubt heard about photon torpedoes and photons and, Star Trek. You're all up on that. For this talk, and for everything I've discussed in the previous talks, we'll treat it as a wave. Occasionally, light will show up as a particle, and then you need to deal with it as a particle. And light is one of these strange entities where it can be wave-like or particle-like depending on what kind of experiment that you do. But you can never see both at the same time. And so electrons are like this, light is like this. It's really a strange thing. It's like having a coin. You've got heads on one side, tails on the other, and you can never devise an experiment to see the heads and tails at the same time. You can't put a mirror behind it and look at the front and the back at the same time. So for these things that I'm talking about today, we'll be dealing with light as a wave. Visible light is a very small part of what's known as the electromagnetic spectrum. It extends from radio waves all the way up to X-rays. All of these you come in contact with basically every day. Your TV remote control works in the infrared. You see in the visible. Ultraviolet is what gives you a sunburn. You cook your hamburger in a microwave. You listen to the radio station. When you go to the dentist, you get your teeth X-rayed. Cosmic rays are coming down and hitting you right now as we speak, going right through your body, maybe making a gene mutation, maybe not, maybe giving you cancer, maybe not. Every day they're hitting you. You don't know about it. You experience the entire magnetic spectrum every day, and this is an incredible spectrum. It goes from 10 to the third in frequency, that's cycles per second, up to 10 to the 15. Let's see what I'm dealing with. This is wavelength here. Frequency 10 to the 6 up to 10 to the 24. 18 orders of magnitude. It's an enormous range of a quantity that you're coming in contact with every day. And only an extremely small part is detectable by our eye as visible light. All right? Now, the other reason I put this light up here is because I didn't tell you what the medium was or how these waves got through nothingness from the sun to the earth. It's very interesting. Electromagnetic radiation. If you make a change in an electric field by moving some charge, an electron, that change in electric field makes a magnetic field. And the magnetic field is changed. And that change in a magnetic field then makes an electric field. And it just keeps on going. It is a set of coupled waves, electric and magnetic, where the change in one makes the other. And the change in the other makes that. And so they just go back and forth, shaking hands. Oh, you're up, I'll go down. Oh, I'm down, you go up. Back and forth. That's how it moves. Electric and magnetic fields. Okay? I won't deal with that anymore today. I could spend a semester talking just about that. Light transmits energy. All right? It's a wave propagating disturbance, but if I put something on the end of that string, I could make it move. I could make it transmit energy. And I thought I wasn't going to be able to get, the Starship Enterprise in here and show you what a photon torpedo would do, but instead I convinced Warren and Emily to provide me with a laser, which I hope I can turn on. A laser which is more powerful than the norm. You might see that they have this locked down here, so there's no way I'm going to grab this laser and move it around. That's because, although it looks like just a red laser pointer, it's more like a lightsaber. We have to do that again, right? That was so good. So the light is coming up through there. You can't really see it, and I'm not going to put chalk dust on it so that you could see it. But when I move the balloon in, it puts a hole in it. So take a look at this spot. You're to watch this spot. What we have is a laser which is going through an aperture. I can use those words now because you all know what it is. And I can change the size. And I'm going to make the aperture smaller and smaller and smaller and smaller. And most people would think, well, the light spot's going to get smaller and smaller and smaller and smaller. Well, as is often the case, so here I have a large hole, and you're seeing the intrinsic size of the laser. And now I'm going to make the hole smaller, slowly, smaller. The light spot is getting weaker, but larger. This is called diffraction. Diffraction is when you put a wave through a constriction that's on the order of the wavelength of it, and I'll define that in a little bit. It actually spreads out. So that those of you who said, I know how to beat this focus game in my first lecture, I'm just going to make the smallest aperture I can and everything's going to be in focus. No, You lose because diffraction actually makes your image blurry. And lenses are diffraction limited. You can actually make the hole so small that the focus of it gets worse. So that's why you don't normally see people stopping things down all the way on their lens, just for that reason. That is strictly a property of waves. If light was, in fact, a beam of particles like baseballs going through that hole, when I close that slit up, the number of baseballs that went through would just get smaller, 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 smaller. Not a property of particles. So I just demonstrated that light is a wave, at least for this talk. Now, why are wavelength and frequency important? Well, the product of them gives you the speed of the wave. And in fact, for light, the speed is fixed if we're in vacuum. But you know that we can reduce the speed of light by putting it in another medium. That's why light was bent, right? We put it into glass. It had a slower speed there, and so it took the path of least time to get from one point to another. All right? Well, that speed is the product of the wavelength times the frequency. And this is extremely easy to remember because you can just think about walking. I take a step length of 1 meter, and I take the period, the frequency at which I'm taking a step might be 2 steps per second. What's my speed? Couldn't be simpler. It's the length of each step times how many steps per second I take it. 1 meter times 2 steps per second, 2 meters per second. That's exactly what this relationship says. The wavelength is the repeat distance in the repeat time, the repeat entity in distance, and the frequency is 1 over the repeat distance in time. In other words, if it took half a second for me to take a step, I would get 2 steps per second would be my frequency. Now, light is fast. The velocity of light in vacuum is 3 times 10 to the 8th meters per second, or 186,000 miles per second. We can reduce that by putting it in water or plastic or diamond. We reduce that. Here are the times, maybe on a scale that you can appreciate a little bit better. It takes light 1.4 seconds to get to the moon, 8 minutes to get from the sun to us, or a nanosecond per foot. And that's actually a very important quantity because your computers nowadays are actually size limited in the length of time it takes for the electrical pulses to move across the chips and the communication parts in your computer. It takes them a nanosecond to move a foot. If they can move at C, they actually have to move somewhat reduced than that. They're trying to make those things smaller and smaller and smaller, so it takes fewer nanoseconds. So that may not be a unit you use too often, but actually it's one that impacts you every day. Here is the visible spectrum of light. That small part of the electromagnetic scale that you can see. You have eyes that are sensitive to wavelengths of 700 nanometers. That's 700 times 10 to the minus 9 meters, 0.7 microns. Much smaller than the diameter of a hair, okay? But still 1,000 times bigger than an atom. So it's sort of in the middle range. You can't see it, but it's not atomic in scale. If we cut this wavelength in half to 35 or 350 nanometers, we're now in the violet. And that's it. You have a factor of 2 in wavelength. Even though the electromagnetic spectrum went 20 or 18 orders of magnitude, 10 to the 18th, you get to see one lousy factor of 2. So we have white light going through a prism being projected on the wall. We never really discussed why you saw the different colors there. Why is it that white light, when it goes through a prism, breaks up into the constituent colors? You should now be able to answer that. The light takes the path of least time. Red light traveling through glass has a different speed than blue light traveling through glass. Blue light is actually slower in glass. All right? Red light is faster in glass, but each color has different speed in the glass and therefore takes a different path in the glass. And so it splits up. So that very first principle that we used, light takes the path of least time, is what causes this dispersion of the colors that are in white light. That's the physical principle that causes this. Now, how is light perceived by your eye? We have this wave. It's going into your cornea through the lens onto the back of the retina, and it focuses a picture, an image. You actually have an image back there. You need to have some receptors in your eye that take that and turn it into an image in your head. And it's very, very similar to what I described for a digital camera. There are sensors back there, rods and cones. The rods sense intensity of light, no color, how bright or how dark. The cones not only sense intensity, but also red, green, and blue. It's exactly like what I described for a camera at the back of your head, right? It then transmits this signal to your brain, and then a whole lot of special stuff goes on in your brain in terms of perception, but the actual mechanics of absorbing the picture are the same. Here's the spectral response. 400 nanometers to 700 nanometers. This was that wavelength of visible that I was talking about before. The blue, the short wavelength, violet down here, the long wavelength was the red. You see that your eyes are most sensitive to intensity right around the green-yellow. That doesn't mean these rods are perceiving green and yellow, but it means that if you had a blue object that was the same brightness as a yellow object, you would see the yellow object better in black and white. Many animals don't have the color vision that we do. They just simply see this way. And this is the object actually of camouflage. If you have a bright orange camouflage suit on and deer have this sort of spectral response and don't have any cones, they don't see you very well. Even though with our eyes, in the color perception, we're quite visible that way. Okay. What is the color response for the cones? So these are the color sensing receptors in your head. There are three types. There's what I will call X, Y, and Z, and they are more or less red, green, and blue. What's a little interesting about this is there's tremendous overlap between these receptors. If a wave comes in and excites the X receptor, you get response that's over here in the blue. In other words, a blue wave can come on and excite X, even though X is, quote, the red receptor. And you can have a wave come in here in the green, and it excites the Y and the Z, but almost none of the X. And so this is the structure, the anatomy that we've grown up with due to evolution. It's not all that surprising that the intensity that we're most sensitive to is also the intensity that's most transmitted down to the surface of the Earth. So when we have sunlight, this is where the maximum power is that's arriving to us from the sun, and so we can see the best there. So I think that's an evolutionary adaptation. And also we'll find out that our color sensitivity right here again in the red and in the yellow-green is maximum by exciting two of these types of cones. I was very surprised to see this big peak in the blue. I didn't know that existed until I started preparing this talk. This is the wavelength at which we have maximum visibility. We don't see fire trucks that are blue, typically, but they're now starting to use blue spotlights and lights sometimes, probably trying to excite this, but they're typically yellow or red for maximum visibility. So the question is, what colors can we perceive? What are all the colors we can see? I gave you that spectrum going from red to green, but clearly with it, not every color is represented there. In fact, we're only showing you the colors that are the technical words are most saturated, the most pure colors. Well, the way to think about this is let's get a normalized value for how much we're exciting the X type of cones in your head, and that's just going to be the X signal divided by the sum of all the signals. With that normalization, X plus Y plus Z, the amount we're citing X, the amount we're citing Y, and Z, all have to add up to 1 because that's how much is hitting you. When we have this equation down here, if I tell you X and Y, you can tell me what Z is. So let's pick the easiest case. X is 1/3, Y is 1/3, and Z is 1/3. 1/3 X, 1/3 Y, 1/3 Z. What color do you think you see? White. You see white. All right. That's what we do for all of these. If I say we have a very large X, that means you're going to have a lot of red and yellow, little bit of blue, not much green in it. If I happen to pick right here, I have Y and Z, but 0 red, then I'm going to get something that's in the blue-green. Well, this was done, this table was made in the 1930s, showing the entire range of colors that the human eye can see. Remember what I said? I said if I made X very small, this is my last example, X was very small, that I had red, or I had the Y and the Z coming together, and I had this blue-green color. So X can get down to 0, and Y in green, Y is about 0.6, that means that we have about 0.4 for the Z. Conversely, if I go way over here and have a lot of the X, that was our red, then I'll have small Y and Z, and this is the color red I get. And then all of the colors that you can see are on this diagram. If I do 1/3, 1/3, Z is 1/3, I get white. Okay? You need to add to this brightness, because we've normalized everything to be 1. You can have brighter or darker colors, but that's the entire range of colors that you can see. The spectrum that you're so used to looking at is the rim of colors around the outer edge. If you take this outer edge and were to straighten it all out, you would have your normal spectrum starting at blue, going to green, orange, red that I showed you before. But you miss all the colors in between that the eye is. Okay? That's what we have to work with. Now we take a picture with a camera, and this is actually a slide that I used last week. We know that some of the light comes in, and we filter it through a blue filter and record its amount. Last week, we weighed the amount of water that went in, right? We add a green and a red filter so that we have red, green, and blue, and we weigh what the relative proportions are of the amount of light coming in, just like your eye does. The difference, however, is the spectral response of the detectors in a camera and that of your eye. Your eye are in the single lines that are being shown here. This is just a replication of Z, Y, and X. This is what the photodetector response is in your camera. And the fact that the red doesn't creep on over here into the blue the way this does, and the overlap is not nearly as large, means that the camera detects colors differently than your eye. And that's a problem when you want to reproduce photos that look the same way that your eye is seeing it, because you have different detectors. We can do a pretty good job of this. Here is RGB, red, green, and blue. And if I can turn this on, here are the 3 separate colors. And this is called additive color mixing. If I take the red and the green and I overlap them, I get yellow. Okay? So what is hitting your eye is green and yellow are coming off of this. They are exciting your X and Y detectors primarily. That's the red and the yellow-green ones. And you're seeing that, you're perceiving that as yellow. If I mix in some blue, blue and red is giving me this magenta color. Magenta, I think is proper. And if I move it over farther, it's not perfect. It was better before. It should be white. Does it look white in the center? Yeah? Okay. You get white when you have the overlapping of all the colors. All right? So red, green, and blue, we know, can make up the colors very nicely. We have yellow, magenta, and cyan. We have white. And when we first came out with computers and we had something like 4-bit color, your monitors were just those colors. And you kids don't remember back when Pac-Man had to be played with, 4 colors. If you had 8 colors on your screen at one time, you had a supercomputer. That's where we started. Nowadays, what we do is divide the red level into 256 levels of intensity. And so if I have, here I have just a piece of film that just varies the intensity, doesn't color anything. So if I lay this piece of film over my red part, you can see that the red gets darker. Let's see if I can get it just where I want it. See, it's just making the red a darker shade of red. Now if I bring that darker shade of red, by making that red darker, I change from a yellow to something that's more like an orange. So if I add in different intensities of red, green, and blue, I can produce more colors. And in fact, here is all three colors being added in of equal intensity. I start out by adding 0 red, 0 green, 0 blue, and I get black. If I add in my 255, 255, 255 red, green, and black, I get full white. And obviously, if I add in half of all of them, I get gray. But now I can do this with each of my three colors. And so that gives me 2 to the 8th levels per color, but I have 3 colors. And so the total number of colors is 256 cubed, 3 colors, or 2 to the 24th, or 16 million colors. And that is that number that you hear when you buy a monitor or you buy a computer and they say, this shows 16 million colors. That is 2 to the 24th. Sometimes they'll talk about it as being 24-bit colors. Sometimes they'll talk about being 8-bit because each of the individual colors is 2 to the 8th of them. What does that mean for you? It means you can get a lot better than you could 25 years ago. These are all the colors. I don't actually have 16 million pixels up here, but it's a lot of the colors that you can display using RGB. Now, 16 million colors is a lot, but how does it compare to your eye? It's not everything. Standard monitors can only reproduce the colors that are inside this bluish purple triangle. Adobe has worked on making a larger gamut, which can include a larger area. Now remember, this is the mechanism by which we're making photos. And if you're taking a photo of a beautiful plant, and those plant's leaves are out there, you don't have that color. You only have the colors that are in here. Now, the percentage of colors is not at all, that you're missing, is not at all proportional to the area in this display. So it's not nearly like, God, I'm missing half the colors. It's not that way. But you are absolutely unable to produce the colors that are outside of this gamut with the standard set of printing that you all have at home if you have a printer or you send it off. This is by no means limited simply to digital photography. Film has exactly the same problem. So does painting. Right? Each of them has a different gamut. Each of them has a different region of colors that they can handle, but none of them have the full spectrum of colors that your eye can see. All right? So those of you that say that, those people that say, well, film gets the colors that I want better, your film, if you're shooting Fujifilm, it's supposed to be very good in the green. Your gamut for Fujifilm may come up here. Kodachrome, Kodak is supposed to be very good in the blues. Might be larger. Okay? You have to pick what you want to work with. So just to show you that I'm not lying to you, we have a magnification of what is going on in this TV screen. So this TV screen is shooting just some sort of white picture to you. But actually, it's shooting to you red, green, and blue, and these are the pixels on that camera. There is a red, a green, and the blue is a little obscured here, but you can see blue. And this is an eye of a needle, just to show you how small they are. So this isn't fake. They actually are red, green, and blue colors on there, and every other color that you perceive outside of red, green, and blue comes from mixing of those three at different intensities. This is how we project it to you on a computer monitor. This is how we store it on a camera. In an array of 6 million or 12 million or whatever your camera has, resolution, number of pixels. But how did we create the light in the first place? Got some hardcore physics here. How did the light get generated? There are two types of light that I want to talk about. One comes from isolated atoms. You have all heard talks on quantum mechanics, no doubt, where people talk about energy levels in atoms. That's what this picture is supposed to show you. That an atom that is isolated can only have its electrons in certain levels, and all the spaces in between are forbidden. They can't be there at all. If I stick a bunch of atoms together to turn it into a solid, like a rock, I actually mix up these levels, but I mix them up in a way where I have allowed groupings and I have non-allowed gaps, energy gaps. You can actually think of putting 1 million of these together and grouping all of these in now to a fat band, having a gap and grouping all these into a fat band, and so you have these bands of allowed states, bands of forbidden states. Turns out these two types of things give you very different types of colors. Whether you are isolated atoms or whether you're in a grouping, in a condensed, in a solid system, you get different types of colors. we have a mercury lamp here, and mercury in a vapor is an isolated atom. And so when we excite that atom, we are making electrons go from one allowed level to another. When they change from one of those allowed levels, they emit light. But they only emit light of a certain color. And mercury has a very strong blue emission and green emission and not much red. Okay? Now, while holding the light on center, look off to the right and left sides. You should see lines. You should see lines off to the right and left, which are blue and green. Okay? Now, as a counterpoint, as a comparison, now you should not see a discrete set of lines, but a continuous spectrum that you all know. All right? Okay, so let's flip some room lights on. What has happened, and this is very, very fundamental physics. This is physics that was at the turn of the century. Einstein was involved in this. We discovered a lot about quantum mechanics when we were doing this. This is the early first third of the 20th century. The individual lines came because isolated atoms, their electrons could move from one allowed level to another. And when they jump, they emit light, but only of one color. Okay? And that's why different atoms will have different colors that are emitted. And so people use this for determining what's that material in that star. Can't go measure it. You look at the light that was emitted from that star, and you can tell by its fingerprint of colors what it is. Now, over here, it's actually more complicated. The electrons are sitting in this big band of allowed levels. They have an infinitely accessible number of levels very close to them. And so they can hit all the colors continuously. So when I had a tungsten filament, and I give this question to my graduate students on oral exams, I have a tungsten filament. Why does it show me a continuous spectrum where tungsten atoms would just give me lines? The difference is one's in a gas and isolated, and one is in a condensed wire. There is a semester's worth of physics in that. So the individual lines, this background, by the way, is just there to show you where it sits in the spectrum. You actually would see a line, and then it would be black. There'd be nothing. And so this is the spectrum from hydrogen, helium, sodium, and mercury. This is what you looked at. I saw most predominantly the blue and the green. It has some, but it's very much shifted towards this. Neon lighting works this way. When you see a real true neon light instead of these fake modern painted ones, it's a red color because the emission is in the red part of the spectrum. If they want to have a light that's blue, they use mercury. If you go to a parking lot and it's all yellow-orange, they're using a sodium vapor lamp because of the very bright sodium yellow peak. Those are two very different types of light. Mostly, your light sources are actually coming from extended objects. Not too many times are you taking photographs of someone being illuminated by a gas discharge tube. It does happen, and I'll show you in a little bit, but most of the time you're actually doing it from extended objects. And so we have an extended object here. It's just a carbon rod. Okay, it's about the size of my finger, and we're going to pass a current through it. A lot of current. I just crank this up, Warren.
Blue tape.
Blue tape. If I go higher than that, I vaporize. Oh, now it's buzzing.
Oh yeah, you're cooking.
So this started out black. Agreed? Now I'm going to run a lot of current through it. If we plunge Ann Arbor into darkness, this is why. Now, unfortunately, that looks, orange to me, and I don't see orange up there. Do I have to stop it down?
There you go.
Okay, that's better. Okay. As dark as we can. Can you still see that glowing cherry red? Just the teeniest bit. When you can just see something glowing, its temperature is about 600 degrees C. Okay, so that's what your oven filaments. Now I'm going to give this thing a little power and start passing current through it. It is getting a little bit brighter. Can you see it's getting a little bit brighter? Maybe not yet. You have to be closer. Now can you see it? And by the time you get up to about 1,000 degrees C, it'll be orange. There's a reason, a very nice fundamental reason why the whole is brighter than the carbon itself. If we could go hotter with this, we could turn this into a blue glow. All right, but not without fire trucks around us. I can do a similar experiment and go higher in temperature here. So you can see that dull glow, 600 degrees. Orange, 1,000 degrees. And as I go up, you should see more orange and yellow. And I can go all the way up until your eye perceives it as white. But actually, you shouldn't be seeing too much blue. Do you see much blue? No? Say no really loud. Great. Okay, why is that? Light that's coming from these large objects where the electrons have many, many levels have a spectrum that's very broad. In fact, this is the visible spectrum starting off at our long wavelengths, red color, going to violet here. That's it. When we're on this side, your eyes can't see it. It's in the infrared. When we're on this side, it's in the ultraviolet. So when I'm sitting at 3,000 Kelvin, which is about the temperature of the hottest that I can get a tungsten light bulb without having the filament break, this is the spectrum that you get. Look how much of the energy, that's the area under here, is out in the in the infrared. That doesn't help you see at all. It just costs you money to Detroit Edison. It does help heat your house, but it is an expensive way to heat your house. This is all the visible light that you're getting right there. And that's why, to conserve energy, we want to be replaced with a different kind of light source, not an incandescent light bulb, which operates about this temperature. If we heat it up to 4,000 Kelvin, which I can't get with a tungsten light bulb, then the green is about the midway. And if I go to 5,000, I find that I'm peaking somewhere right around the yellow-green. The sun, the surface of the sun, is about 5,500 Kelvin. All right? And that's the peak in this, and that's the light that has the maximum energy that's hitting the Earth. So the sun acts as a black body radiator with 5,500 Kelvin emission. This has enormous impact for photography, enormous impact. Light sources that will be illuminating your subjects: clear blue sky, 10 to 15,000 Kelvin. Overcast sky, 6 to 8 Kelvin. Noon, 6,000. Average sunlight, I said 5,500. Electronic flash, household lighting, 2 to 3,000 Kelvin. Candle flame, 1,000. These are all sources of light that you could use for your subjects. Your eye, actually your brain, uses these lights to see white. So when you read a book under a tungsten light, you think you have a white page. When you read light out under a clouds, you think you have a white page. If you're under a blue sky, you think you have a white page, even though the source, the temperature of the source of light has varied from 2,900 up to 10,000 Kelvin. Your brain handles it. Camera can't do it. And this is incredibly important. So here is that what your eye can see, and this locus of color temperatures is this line. So we start off at red, down around 1,000 Kelvin. We go all the way up to, if you have an infinitely hot source, you will see it over here in the blue violet. Now, why isn't it off scale? Well, you can't see off scale. You move it as far to the high frequency as your eye can see. Why is it blue and not violet? The sensitivity of your eye goes down in violet. That's why you see blue. So even if you had something that was emitting X-rays and gamma rays and all these things you can't see, you're going to see it as blue. Here is the identical picture. I only took one picture, but I told my camera that I had a 2,900 Kelvin source. I have a 5,000 Kelvin source and a 6,700 Kelvin source. Look at what the camera does with this picture. This was actually taken under a light in my kitchen, so it's a tungsten bulb, so it's close to this 2900. It gets the back card kind of white. It gets the flower white. If I told it now I was taking it out under sunlight, it's the wrong color. Likewise, if I told them out under open blue sky, the colors are completely different. Look at the blues. Look at the reds. They're just completely wrong. There's a switch on your camera where you have to tell it, what light am I taking my picture under? And if you tell it the wrong thing, you are fatally hurt with those pictures. It's non-recoverable if you're shooting JPEGs. All right? If you have film that's been balanced for tungsten and you shoot it outdoors, you will never recover from that mistake. So the temperature of the light that you use is an incredibly important feature in how your photographs are going to appear. Now what I've done is I've taken these pictures under flash, fluorescent, and clouds, and I've told my camera flash temperature, fluorescent temperature, cloud temperature, and let's look at the comparison. So we do much better at getting white for each of them. The white is kind of white. Look at the difference in the purple and the blue, however. I mean, we just completely blow that. And so photographers that want to make a relatively, honest representation of what they see have to be very careful about the color temperature they use. The reason I'm having such trouble here is not only do I have flash, but I forgot to turn off the tungsten light at the same time. I have two light sources, and they have two different colors, and there is no way to make this look right. Let me switch it. So I've tuned it for the flash. Let me tune it now for the tungsten part of it. Now I get my blues a little better, right? My blues and pinks are a bit better, but look at my white. That is an irreparably wrecked photo. You can't use it. Now, where this really becomes a problem is not all light sources are in fact black bodies. Fluorescent lights were the dominant presentation of this. Us older folks remember walking into a fluorescently lighted kitchen and all of us looked green, right? Your eye could not deal with the fact that the light that's coming out of those bulbs is not a black body light, and your brain could not do a black body adjustment for it. It had too much green, and we all looked sort of sickly. Now, I was talking about this in one of my classes, and I was talking about non-black body emitting objects. And this student quite earnestly from the back of the class raised his hand and says, I have this pair of glow-in-the-dark underwear. Is that going to be a black body emitter? And I said, no, I don't think that's going to be a black body emitter, and I don't have a whole lot of experience with that subject, actually. Now, I feared, however, that someone in this audience would have that same question. And so I had to do some research on this. And if you go online and you search for glow-in-the-dark underwear, it brings you all over. Places you don't want to be. So I made another very dangerous excursion this morning. I went into my teenage son's room looking for something. We will spare no risk for this lecture. And I didn't come up with any glow-in-the-dark article of clothing, but I came up with glow-in-the-dark handcuffs. I suspect my son and this other student could have been getting together with the underwear and the handcuffs. I also found a lizard, probably from his younger days. This is decidedly non-black body. It has a greenish tint to it, just like the spectrum that I showed you here. They have worked very hard now to make fluorescent lighting be black body-like. And I'll show you that. You can take a look at this. So I showed you a gas discharge tube. I showed you a tungsten filament. Now I'm going to show a new, modern fluorescent light bulb. Look at this with your diffraction grating. You should see a rather broad spectrum with some sharp parts that are brighter than the others. Do you see some sharp lines in it? they have worked very hard over the past 15 years to make the phosphors in this have a wide spectrum that replicates the sun without having that greenish tint, that greenish overload. And so nowadays, we just realized, by taking pictures of this and looking at the spectrum, that really there's been a tremendous improvement in the technology of lighting. And so now when you walk into a kitchen, you don't get that sickly green cast that we used to have later. Color of the sky. Everyone knows the sky is blue. Sky is blue. How many people know why the sky is blue? Right, a few hands. Well, you'll know in a little bit. Problem is, the sky isn't always blue. It's also orange. But it's not always orange. Sometimes it's red. Sometimes the sky is white. This was taken from Mount Fuji in Japan, but the Great Smoky Mountains. Great Smoky Mountains. That's clouds and fog and particulate. And sometimes, of course, the sky is many colors. All right? So why is the sky blue is not really a great question, because it's also all these other colors, and we have to explain them all. Right? Let's start with why is the sky sometimes blue. All right? The sunlight coming in from the sun comes in a bunch of parallel rays, all of it having this temperature of about 5,500 Kelvin, which means it has a broad spectrum. Has all those colors that you saw coming from the tungsten light bulb. The thickness of the atmosphere, although there's no definite end to it, is predominantly done, something like the 60 some odd % of it, is done about 15 kilometers above the Earth. Radius of the Earth is 6,400 kilometers. With a little bit of geometry, you can determine that at noon, sunlight has to traverse 15 kilometers of atmosphere. But at sunset and sunrise, the sun has to go through 440 kilometers of atmosphere. So we increase the travel distance by 24, 25 times through the atmosphere. Now, what does the atmosphere do to light? Well, we know over short distances the atmosphere doesn't do much, because where I stand far away from an object and close to an object, we see basically the same thing. But over 15 kilometers or more, over 400 kilometers, the atmosphere actually scatters light. And it scatters the colors differently depending on what their color is. So here I have a ray of light going through just the atmosphere. And these are meant to be molecules or collections of molecules. It's very small, smaller than the wavelength of light. The blue is scattered much more predominantly than the red or the green. What does that mean? Look at that tube. We have a light which is going up through water that we have put very small particulates in, much smaller than the wavelength of light. The light comes up in the water, and the first thing that's scattered out of it, which is scattered much more strongly, is the blue. And so if you look at this leading edge of these particles, you see blue light coming out to your eye. Remember, you aren't projecting anything out from your head to that. The light has to come to you. So what the light comes up here, gets scattered at 90 degrees, and goes to you, and it's blue. We're taking the blue out of the light as we go up. And so what you finally see at the end, even though it's not scattered as strongly, is all we've got left is red light. A sunset is what's coming out the end of this tube. Do you see the sunset? That's all that's left, is the red light coming out. So if you are having the light go over your head, like midday, and you're seeing light that's bouncing down at you at, say, like 90 degrees, you're seeing a blue sky. That light, if there was no scattering in the atmosphere, to go right past you, and you have a black sky, just like on the moon. But it doesn't. It gets scattered, goes down to your eye, and predominantly, we can flip a light on, predominantly it's the blue that does that, the short wavelengths. If you're looking end on, and all the blue has been scattered out of it, then you're looking at a sunset, and you see red. This is called Rayleigh scattering, and it all comes about because of the fact that shorter wavelengths are scattered to the 4th power better than longer wavelengths. That means that the blue is scattered, remember there was a factor of 2 between red and blue, 2 to the 4th, 10, 16, Okay? 16 times better. That's why we have a blue sky. That's why we have red sunsets. Another interesting factor about this scattered light is it doesn't come out with the same polarization. Polarization, I said we had a wave. Polarization amounts to which way is the wave waving. If they're all waving in one up and down plane, we say that's a polarized wave. Light that comes from scattering is actually polarized. And so if I have something here, a wave coming in for any direction, but I only allow waves of one direction through, then I have a polarizer. So my wave is coming at me and has all different types of lines, but I'm only letting one type through. Depending on how I orient what I allow through, you should be able to see this get, is it darker now? Dark, light, dark, light. Mr. Polaroid became a billionaire because of this. This is what's in your sunglasses. This is what darkens the sky. It also has the glare also works the same way, is preferentially polarized. In photography, you often want to make a better contrast between your sky and clouds, your sky and buildings. And this is the same picture, just with a polarizer changed. The sky is much darker here because I've adjusted the polarizer. It's a very useful technique. Here is one taken out in the mountains where I've tried to accentuate the blue sky from the white tree as maximal as possible. All right, so you can almost turn the sky completely black. What about white clouds? All right, clouds are not blue. They have a different type of scattering. Here, once again, sparing no expense, we are forming clouds for you, and they are white. All right? Rayleigh scattering is not what's going on here. Something called Mie scattering is going on. And the difference is these particles are larger than the wavelength of light. They're little droplets of water. Now, what color is water? It's clear. Water is clear. But when you put it in little small particles, they scatter light, and they scatter light of all wavelengths equally. And so you see white. Whereas the small particles scattered the blue much more strongly than the red, and you got color separation. But clouds don't do that. Here is an example where we're seeing Mie scattering all over the place. You have Mie scattering from the geysers. You also have Mie scattering from the snow. Once again, they're made of water. Water's clear, right? But you have scattering, Mie scattering, giving it the color. Now, I've just been telling you the color of water is clear. Well, I've been lying. Over short distances, water is in fact clear. But if we look over longer distances, it's clearly blue. What's going on there? Water is a tremendously unique subject. It absorbs in the red. It has an absorption that if you look over long distances in water, it just gets rid of the red. It doesn't scatter it away, it absorbs it, all right, leaving only the blue. But of course, that's not the end of the story, because clearly water is also green and turquoise. Where's that coming from? Well, you can have particulates in water. You can have silt and dust, right? And that can reflect light from varying depths. So if you reflect light from the surface, you're going to see just normal blue light coming from the sky being reflected. But if it reflects off some sand or silt that's farther down, it's had the red taken out. Now it starts turning into something that's more green-like or turquoise. And if you go longer, deeper even yet, it's into blue water. So as the depth goes out, as we take more red out of it, you change the color, giving the Caribbean Ocean its nice properties. Here's water that's blue and black. Clearly what's going on here is the water is reflecting the sky. So the color of the light that's coming in plays a role on water. So what is the color of water is a very complicated question photographically. Once again, reflected light. Now the water is orange. So when someone says water is clear or water is blue, that's not the end of the story. It depends on how you're looking at it, over what length, what is your source of light. You have reflection, absorption, transmission. You can also even take pictures that are outside of the visible spectrum. You can have lights and film that are sensitive in the infrared or sensitive in the ultraviolet. Here is a picture taken by David Lyons, who's attending the lecture today, taken in the infrared. You see the sky is turned black. You should know why. Infrared is very long wavelength. How much scattering occurs for very long wavelengths? Almost none. And so with infrared detection, the sky doesn't look blue anymore because there's nothing scattering in the infrared. That's why it's black. But it scatters quite strongly off of the tree leaves. And so you can look outside of the visible spectrum with film and CCD detectors, allowing you a whole other world to take pictures of. We have one last experiment. I think this is our last experiment. I think we're going to need to kill all the lights. Okay. Wave. Okay, now let's turn on one light so we can see what's going on. We're using a light source that has infrared light. You can't see it. It's very bright, but you can't see it. And we're illuminating him with infrared light, and then we're detecting infrared light with a camera. And he looks plain as day in a completely dark room. You can think of all the uses for this. Certainly it's being used for surveillance. You can illuminate walkways with infrared light. People think they're operating in the dark, but they're not. So now I just want to show you 15 pretty pictures that use light. Okay? You ready? Okay. What is the subject of these pictures is light. It's not the trees, not the water. It's not the wave, it's the light. Me scattering and Rayleigh scattering. All right, so this ends my set of pictures and gets us to the next lecture, which will be by an expert on lighthouses and Fresnel lenses. Photography to paint with light. I hope these 3 lectures have helped you to appreciate that what goes on, it's a combination of art, science, and technology, and thank you very much for attending.
Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program. Local broadcast is made possible in part by Pfizer.